Okay, in this problem, we have an observer that's 26 meters above the ground floor of a large hotel atrium looking at a glass-enclosed elevator shaft that is 21 meters horizontally from the observer. Okay, so here's the observer. They're saying that if they're looking at this elevator, they're 21 meters away. Okay, the angle of elevation of the elevator is the angle that the observer's line of sight makes with the horizontal. It may be positive or negative. So it would be positive if the elevator is up above where they're observing. It would be negative, this angle, if it's below where they're observing. Okay, assuming that the elevator rises at a rate of 7 meters per second, what is the rate of change of the angle of elevation when the elevator is 19 meters above the ground? It also asks us this. We'll come back to that. Okay, but right now we're just going to look at the 19 above the ground. Okay, so it told us to make a little sketch. It gave us a little triangle here. I'm going to make that a little bigger for us to look at. Okay, so there's the observer, and there is the elevator. Okay, so this is the elevator. This is H, 21 meters. This is theta. Okay, so I'm going to add a little bit to this triangle. I'm going to go down a little farther because we know that the elevator is how far above the ground? Well, it says 19 above the ground right there. So this right here is 19 meters. We also know that the observer looking at this elevator that's right here is how far above the ground? 26 meters. Okay, so I'll say this is 26. Okay, based on that, we can figure out what H is. Okay, H in this particular problem, not in the when elevator is 47, but in this one, when the elevator is 19, we can say H is equal to 26 minus 19, so H is equal to 7 meters. Okay, that's pretty important. We'll have to use that later. Okay, for now, let's look at the triangle and let's make an equation, some sort of formula that we can relate these three things. We have theta, we have 21, we have H. Okay, so that's opposite and that's adjacent. So the relating equation is going to be a tangent theta, which is opposite over adjacent. So H over 21. Okay. Quickly on the side here, I'll do this in a different color. We can figure out what theta is. Since I just figured out what H is, I can also figure out what theta is. If tangent theta is equal to 7 over 21, which is what we specifically found it right over here, then we can say that tangent inverse of 7 over 21 is equal to theta. Okay, so that's also important. That will come back later. Okay, one other piece of information that I want to write down before we proceed in this problem is the change in elevation of the elevator. Like how fast is it moving up and down? Okay, that information was given in the problem. It says right here, the elevator rises at a rate of 7 meters per second. Okay, so the elevator's height is given by h, so the change in height is given by dh dt. Okay, so dh over dt was also given in the problem. It's 7 meters per second. Okay, so those are three pieces of information there that will be needed in this problem. Now let's proceed. Okay, so in related rates, of course, we're dealing with rates, so we're going to take the derivative. So let's look at this tangent theta. The derivative of tangent theta is secant squared theta, and I'll say d theta dt, because we're taking the derivative of a theta with respect to time. And then on the other side, we have an h as our variable. So when we take the derivative of h, it's just like taking the derivative of x when you have dx dt or dx dy. It goes away. So the 21 doesn't on bottom, so we get left with 1 over 21. The h, the derivative goes away, turns into a 1, and then it's dh over dt. Okay, we're actually almost done with this problem now. So what we need to do is solve for d theta dt. Now, we've already solved for theta, right? That's right here. That's something you could type into your calculator and get a numerical answer. We've solved for dh dt. That was given in the problem. We solved for h. That was given when we did the 26 minus 19. Okay, so we have everything that we need in this problem. We just need to solve for d theta dt. That's what we're looking for. So I solve for d theta dt, which means dividing the secant over. So I get 1 over 21 secant squared theta dh over dt. Okay, so I'll plug in the dh dt, I'll plug in the theta, and then I can put it in my calculator and get an answer. Okay, so this is going to be equal to 1 over 21 secant squared, and instead of writing theta, I'm going to write what I solved for. Now, if you want to go ahead and type this out and get a decimal answer before you put it in the equation, that's fine. I'm just going to write it this way. I'll put it all in the calculator at once. But if you want to get a numerical answer for that, that's fine. Okay, and okay, so that gives me my theta. Now the dh dt is 7. Okay. All right, so let's go ahead and type that in the calculator. Okay, so when we have secant squared, if you have some calculators, you can just type in a secant squared. We don't have a calculator you can do that, so I can change the secant squared into a cosine, and I can move it up to the top. Okay, so it would become cosine squared of tangent inverse of 7 over 21 over 21, because this doesn't go up with it. It's just the secant that goes up. So the secant squared becomes a cosine squared, moves to the top, times 7. Okay, now I can type that in. Okay, so cosine of tangent inverse of 7 over 21. And that takes care of my second parentheses. Make sure and square it. Okay, so remember, when you have a cosine squared, you can just put parentheses around and put a big square on the outside. And that's what I did here. And then times 7 divided by 21. Okay, and we get 0.3 as our answer. 0.3, and that's in degrees. So d theta dt is equal to 0.3, and that is in degrees. If the problem wants it in degrees or radians, that does make a difference. Since we were, well, it didn't say, so we could do radians per second or degrees per second. Let's change over to radians and get the answer that way. Okay. 0.3. Okay, so that's radians per second. Okay, now how would I go about doing the other problem? Well, it's a simple change, a couple simple changes. If the elevator is at 47 meters above the ground, okay, so that would end up being, that would change your h. Okay, so if this was 47, it would be above, obviously. So 47 minus 26. So h is equal to 47 minus 26, which will give us 19 meters. Okay, given that we have 19 meters, that would also change our theta. So in the theta, remember, to find the theta, we did tangent theta equals 7 over 21. Okay, so the 7 came from subtracting, just like we just did. So instead of 7 over 21, the theta would be tangent inverse of 19 over 21. So tan inverse of 19 over 21 is equal to theta. Okay, the dh dt is still the same. It's still 7 meters per second. Okay, and then when we pop that all in to the equation here, we could just change a couple things here. Let's see, the 21 doesn't get changed right here, but the 7 here would get changed. That would be 19 instead of a 7 right there. Okay, and that would be pretty much, that's the only difference. So for the second problem, d theta over dt equals 1 over 21 secant squared and tangent inverse of 19 over 21, close parentheses, times a 7. Now you can pop that into your calculator just like we did the other one, and you can get your solution.